Hello everyone. Welcome back to the week 9 of NPTEL TA Live interaction session for the Rapid Manufacturing course. The course ID for this course is noc22-me74. This is Palkin Gupta, PhD scholar and a PMRF scholar in Department of Material Science and Engineering, IIT Kanpur. The course instructors for this course are Professor J. Ramkumar and Professor Amandeep Singh, Department of Mechanical Engineering, IIT Kanpur. So, since almost two-thirds of this course is now has passed, so I hope you guys are enjoying the learning process along with these interaction sessions. So, in this week's lecture, what we had covered is the beam deposition process, the various techniques relevant to it, and the materials that are relevant in rapid manufacturing and systems. So we'll go through them briefly first, and then we'll discuss some of the sample problems that will help you in solving your weekly assignments. So what is a beam deposition process? So in beam deposition process, as the name suggests, you have a beam which helps you in deposition of the material. Okay, so there is a beam which helps in the deposition of the material and melting of the material. Helps in material melting and deposition. So now this beam can be of different types. It can be either light or in the form of photons, which are packets of light, or it can be electron, or it can be plasma, or it can be ions. It can be basically anything that will eventually interact with the material and generate heat. And this heat is then responsible for melting and consolidation of raw material to form fully dense part. All right. Okay. So these are the different kinds of beams that are used and what they do. So on the right is the schematic of a basic beam deposition process. You can see there is a laser beam. So this is your laser beam, this pink colored one, which is traveling, and this is your galvanometer controlled optical system. All right, so this basically guides where this laser beam will travel. Okay, and then you have two powder feed nozzles from where your powder is being ejected, and then you have this is your substrate, and all this is your deposited material. Now we have to make sure this deposited material, we have to make sure that in beam deposition processes, it is not that there is a pre-laid material or a pre-laid layer of powder. Instead, there is simultaneous ejection of powder and laser beam. Okay, so the powder is not pre-laid onto the substrate. So BD processes are not used to melt a material that is pre-laid in a powder bed, but are used to melt materials as they are being deposited. So as this powder is being fed onto this powder bed or onto this substrate, this laser is interacting with these powder particles during their flight itself, when they are in the flight motion, and in the during their flight itself it melts them, and then that melted powder falls on the substrate and solidifies. So the different materials that can be used in beam deposition processes are metals, ceramics, or polymers. So almost all kind of materials can be processed using this beam deposition process. So majorly this process has been developed for metals, and hence it can also be termed as laser metal deposition process. Okay, so this can be also termed as laser based metal deposition, since this process has been majorly developed for metals. But here we'll be talking in generic terms and will not confine it to metals itself. Okay, so let us go on to the next slide, where they are talking about the different uh, parts of this beam deposition system. Okay, so in this beam deposition system, the most common type is the metallic deposition, as we had been talking about. Now, there is a deposition head which is used to deposit the material onto the substrate. Okay, so this deposition head is basically responsible for depositing the required material onto the substrate. So this deposition head consists of laser optics. So its function is to focus the beam, which can be your light, plasma, electron, or ion beam. It focuses the beam onto the powder particles or the required locations as per the CAD geometry. Alright, then we have the powder nozzles. So here you can see these two are the powder nozzles. Alright, these two are your powder nozzles. So from these two powder nozzles, your fine powder particles are being ejected into the system. So these are being ejected in a coaxial manner. Ejected in a coaxial manner. Okay. So, and as they are ejecting, and this blue part is your laser beam. So they are interacting at this point, and when they are interacting here, heat is being generated. So now what this heat will do, this heat will eventually melt these powder particles. This melts these powder particles. Now for metals or any material, since this melting temperature is high, there are high chances of oxidation. So there is an inert gas tubing or shielding gas. So this inert gas tubing prevents the oxidation of powder particles. So if this oxidation is not prevented, it will lead to degradation of the properties. Okay, if oxidation is not prevented, it will lead to degradation of the uh, properties of the powder, or the final part you can say. So it can cause corrosion effects, since oxidation is relevant to corrosion. So it will cause your decrease in the strength, decrease in stiffness, increase in porosity, like that. And then this deposition head sometimes consists of sensors as well. Okay, so these sensors sense what kind of deposition is being done, or how melt pool is forming, what is the pool depth, etc. So the function of sensors is to sense all such activities. It is basically an optional part. It is not a necessary part of any kind of deposition head. Okay. So now in this is the substrate. So this substrate can either be a flat plate or an existing part onto which additional geometry will be added. For example, this can be something like this is a pre-existing geometry. Okay, this red part. This is your pre-existing geometry. So your powder particles can be laid onto this as well. Your material can be deposited onto this geometry as well. So this is your material 2. So this functions similar to the laser cladding process. This is laser cladding, wherein you form clads or coverings of second material over the first material using laser deposition technique. Okay. So now let us see some key points about this beam deposition process. So this deposition is controlled either by the motion of the deposition head, or by the motion of the substrate, or by a combined motion of both substrate and uh, deposition head. Okay, so for example, this is your substrate and this is your deposition head. Okay, this is your deposition head. So either you can move this substrate, or you can move this deposition head, or you can have a relative motion between the two. So when you have a relative motion between the two, you get a wedge like geometry. So what I mean to say is, you can control the geometry of different parts using the relative motion between these substrates and the deposition heads. Now also, this deposition head can be mounted on a 3-axis device, or a 4 or even 5-axis device. So in 3-axis deposition head, what you have is deposition of material in vertical direction. Okay, but in case of 4 or 5-axis deposition heads, you have you also allow for rotations. And now these rotation heads can help you in the formation of preform objects. Okay, so the objects that are having a very complex contours. Objects having complex contours. Okay. For example, the contours as they are present in your teeth, or as the contours present in the skulls, like that. Okay. Now, the second point is the kinetic energy of powder particles being fed into the melt pool is greater than the effect of gravity on these powders during flight. Okay, so what we mean to say here is, whenever there is a melt pool, obviously there will be buoyancy effects within the melt pool. Okay, so there are buoyancy effects within the melt pool, and these effects causes density difference. Okay, now because of this, your powder particles can move and come towards the surface. Okay, so this can cause the powder particles in the melt pool to move out or upwards. So now at this point of time, the incoming powder particles having higher kinetic energy will strike on these and will force them to move towards the melt pool. Okay, so in that way, your the stability of the melt pool is kind of maintained. Okay, next point is large thermal gradients should be avoided. Okay, so large thermal gradients should be avoided to avoid warpage. So if you have controlled thermal gradients or low thermal gradients, what you get is a flat object. But when you have very large thermal gradients, okay, so very large thermal gradients will cause warpage. So what your object will be like, it will kind of bend. So this is your warped object. So we never want a warped object. Why? Because why does these objects warp? Because whenever there are large thermal gradients, what it means is large thermal gradient means uh, very large temperature differences at different points of the object. So, because of this large temperature difference, your heating or your cooling rates will be different. So, this will result in different cooling rates. And the difference in cooling rates, like suppose the cooling rate is faster here and it is slow in the middle and then again fast at the corners. So because of this difference in cooling rates, what will happen is you will be having unequal expansion and contraction of the material. Okay. Now, because of this unequal expansion and contraction, what happens is at one point uh, the material has contracted fastly and at other point it hasn't. So it will distort the geometry. So where this is slow, suppose here it is having slower dimensional change, but here the cooling rates are fast. So it will have faster contractions. So then there is unequal contraction and this will kind of not have equal value. This is not having equal values, hence it distorts the geometry to accommodate the difference. So hence there is distortion in geometry to accommodate the difference. All right. Now, next point is control of microstructure by controlling thermal gradients. So, by controlling thermal gradients, you can even have microstructures similar to the cast parts. Okay, cast like microstructures. And just by controlling the cooling rates, you can have columnar microstructure or lamellar microstructure or dendritic microstructure, etc. So this control over microstructure basically gives us a control over the mechanical properties as well, because the microstructure majorly defines the different kinds of properties of any material. So this control will eventually help us in tailoring these properties. Now, overlap of consecutive layers to ensure good bonding. Okay, so the amount of overlap is typically 25%. What happens is the consecutive layers, different layers, should have some kind of overlap. Okay, so I'm giving you a front view kind of a thing. So if this is your front view and this is your one track, this is your track 2, this is your track 3 and 4. 1, 2, 3 and 4. So now when your track 2 is being deposited, 25% of your track 1 should be melted. So this portion should be melted. Now why so? If it doesn't melt, then you will be having only this kind of a point contact. But if it melts and solidifies with the second track, what will happen is you are going to have a better bonding. Okay, so when this melts, it will then join with the second layer and second track and solidify with it. And when such a kind of solidification happens with such an overlap, you have better strength at the interface. This gives us better strength at interface of two tracks. Okay, and also this overlapping is done in consecutive layers as well. So suppose this is your first layer and this is your second layer. So when the second layer is being deposited, some part of this first layer is melted. Okay, this is melted, or this is what is overlap, so that the second layer joins well with the first layer without any kind of interfacial loss of strength at interfaces. Okay, now we come to the material delivery. Material delivery is basically the delivery of the raw materials. It is delivery of the raw material to the substrate. Now, in beam deposition processes, we can use either powder or wire. So, both powder and wire feedstocks are utilized in beam deposition processes. So, we have powder and wire feedstocks. So, first we'll be talking about powder feeding. Okay, so on the left it is a schematic of a powder feeding system. So each one of them have their own benefits and drawbacks, and we'll be looking at them in a sequential manner. So this powder feeding system or powder feedstock, this is the most versatile one, as both metal and ceramics are readily available in powder form. Okay, both of them are available in the powder form. Okay, so we have seen this is your process direction, or the direction in which your deposition head is moving. Okay, now this is your powder feed nozzle, and here this is your powder stream, which is inclined at an angle A and is at a distance of D from the substrate. Okay, now this is a shielding nozzle. It means it provides shielding gas to prevent oxidation. Alright, and this is your laser beam, and this is your deposit, and this is your substrate. Now, beam deposition processes using powder feeding can enable overlapping scan lines to be used without the swelling or overfeeding problems inherent in extrusion-based processes. We have seen in some of the previous lectures how there is swelling or overfeeding problems in FDM processes or extrusion-based processes. Now, this problem is avoided in case of beam deposition processes by the method of simultaneous powder feeding. Okay. Now, here it is to ensure that all the powder that is being fed is not captured. So, we can say that powder capture efficiency is less than, sorry, it is just less than 100%. That is, some of the powder is not captured in the melt pool. Okay, so now the care must be taken that you initially you provide some excess powder so that there is no shortage of powder. So excess powder is fed, and care must also be taken that whatever excess powder is being fed, that is taken out without any loss or degradation if you are to recycle that powder. Okay, so that excess powder should be recaptured in a clean state. So excess powder should be recaptured in a clean state. Okay, and this excess powder is not a negative thing. Okay, it's not negative. Okay, you should not feel like feeding extra powder is a kind of negative attribute of this particular system. Actually, it is not. Okay, why? Because it enables the melt pool to change its size dynamically. It enables the melt pool to change its size dynamically. Okay, so this dynamic change in melt pool size will eventually help in better joining or better fusion of different layers and tracks. Okay, now let us talk about the energy density of the beam in these beam deposition processes. So this energy density of the beam must be above a critical level to form the melt pool. Okay, so it is necessary that the energy density of the beam is above certain critical level to form melt pool on the substrate. All right, so let us see the schematic of the laser optics and energy density terminology. So this is your focusing optics, which is causing you to focus the laser beam. Now, this is your entire energy beam density which is required for melting. So here is your focal plane in which it is being focused, and this is the buried spot region and this is the exposed spot region. And melt pool is formed in this entire region, which is of some few millimeters. Okay. So basically what we mean to say is there is a region above the focal plane and below the focal plane where the energy density is high enough to form a melt pool. Okay, so this region is enclosed within these green lines, okay, where melt pool is being formed. So if your substrate surface is either too far above, so if it is too far above, say somewhere here, then the melt pool will not form on the surface, or if it is too far below, say suppose it is here, then also the melt pool will not form. So the surface of the substrate should essentially lie within this area. Okay, only then the melt pool will form. Okay, so if the substrate surface is either too far above or too far below the focal plane, no melt pool will form. Similarly, the melt pool will not grow to a height that moves the surface of the melt pool outside this region. Okay, so within this critical beam energy density region, the height and volume of the melt pool is dependent upon the melt pool location with respect to the focal plane. Okay, so what is the location of this focal plane with respect to the melt pool decides the height and volume of the melt pool. Okay, so the location of the melt pool with respect to the focal plane decides the height and volume of the melt pool. Okay, now how is powder fed? Powder is typically fed by first fluidizing a container of powder material. Okay, so fluidizing a container of powder material, what does it mean? Like making the powder so that it starts flowing easily. So when you it can be done by bubbling up a gas through the powder, and what it will does is it will just enable the powder particles to loosen up and cause them to flow easily, and then they use a pressure drop to transfer the fluidized powder from the container to the laser head through the tubing. So when there is a pressure drop, so the powder will automatically start to flow because of the pressure difference from the powder container to the laser head through the tubing which has been provided into the system. Okay, so now we have different configurations of powder feeding. So one of them is this coaxial nozzle feeding. So the name suggests coaxial. It means the powder is coming in a coaxial manner. Okay, so the powder is introduced as a toroid surrounding the laser beam. Powder is introduced as a toroid surrounding the laser beam. All right. Now which is focused. Now this is focused to a small spot using a shielding gas. So here you see this is your laser beam, and this is your coaxial nozzle. So it is kind of a 360-degree mechanism, and from here your powder is coming. So this is given by this, and here it interacts with the laser to finally melt and deposit on the substrate. And also this is your shielding gas. So this is your powder, and this is your shielding gas, which prevents the oxidation. So it basically forms a cover over this. Okay, now another one is your single nozzle powder feed. Okay, so another configuration is single nozzle powder feed. Okay, here you are having a single nozzle, that is a separate thing, and a laser beam. Okay, so they both work independently of each other, but such that they interact at the point of a substrate. Whenever they like reach the substrate, they interact with each other. So what are the benefits of coaxial feeding system or a single nozzle feeding system? Let us see that one by one. Advantages of coaxial nozzle feeding. Okay, now what are the advantages? First is it enables higher capture frequency of powder, sorry, higher capture efficiency. And second advantage is focusing shielding gas can protect the melt pool from oxidation when depositing in the presence of air. It is to bring to your attention that there is no shielding gas system in this single nozzle powder feed system. Now let us see what are the benefits of using single nozzle powder feed system. So advantages of single nozzle powder feed. Okay, let us go through them. First is the apparatus is relatively simpler apparatus. Second is you have better powder capture efficiency, better powder capture efficiency than four nozzle feeding. And you have the flexibility or ability to deposit material into tight locations. Tight locations means hard to reach locations, or in complex geometries where you have very small locations. Okay, now you have another system which is four nozzle feeding. Here you have four separate nozzles which are equally spaced at 90 degrees. So this is your head, so these are your four different nozzles at 90 degree, and they like feed the powder to the system. Okay, and they are focused at the point of intersection of the melt pool. Okay, now another system is wire feeding. So the major benefit of wire feeding system is you have 100% capture efficiency. Okay, so 100% of the feedstock it is used, and so this is very effective for simple geometries, coating of surfaces, or places where porosity is acceptable. So used for simple geometries, simple geometries, coatings, and deposits where porosity is acceptable. Okay, so this is a typical wire feeding system where you have this electron beam, or you can have a laser beam instead of this. Then you have this wire feeder. It feeds the raw material in the form of wire. Then you have this molten metal. This is your molten part. So this is your molten part. Then these are your previous layers, and this above is your uh, like resolidified alloy. Okay, so this is your wire feeding system. Okay, so basically when you can accept the porosities in the system, this is used. All right, so this was about your beam deposition processes. Okay, now next is, let us look at some of the process parameters in this beam deposition system. So first is the track scan spacing. So now what is this track scan spacing? So suppose this is, you are looking at this object from top and you have different tracks. So these are your tracks or layers. So the distance between these two from center to center, this is known as your track scan spacing. Center to center. Next is powder feed rate, the rate at which you are feeding the powder. Laser traverse speed, the speed at which your laser is traversing. Then your laser power, laser spot size, and your scan pattern. So these parameters, all of them or some of them at least, are interrelated to each other. These are interrelated to each other. Can any one of you tell how these are interrelated? For example, how is your laser power and or powder feed rate are related with your traverse speed? Can any one of you answer? Okay, so increasing laser power or powder feed rate and decreasing traverse speed will increase the deposit thickness. So if you increase the laser power, okay, increase the laser power or a powder feed rate. So if this means you are increasing the size of your melt pool. So you will be having larger amount of powder, and increasing the laser power means increasing your energy density, therefore your the size of your melt pool will increase. Okay, increase in melt pool size. And when you decrease your traverse speed and decreasing the traverse speed. Now, when you decrease your traverse speed, you'll be spending more time at one particular location. This means you will be spending more time at one particular location. Okay, so when you spend more time at one particular location, then what will happen? It will be exposed to the laser for a longer time, and hence your melt pool size will increase again. So you see these have similar kind of effect, and hence this will increase the deposit thickness. Okay, so this is how these parameters are interrelated. Okay, so now a scan pattern also plays an important role in minimizing the residual stresses. So that is why it is often tried to change the direction of laying up the material in different layers so as to reduce these residual stresses. Okay, so for example, if first layer is scanned in suppose x direction, say this direction, so your second layer shall be scanned in y direction. So hence in this manner your residual stresses are reduced, because in first layer they will be in x direction, in one direction, in second layer they will be in another direction. So hence there is some cancelling of the stresses by opposition in in their directions. Okay, so now lastly we'll see some of the benefits and drawbacks of these beam deposition processes. That some benefits are that it produces fully dense parts with controllable microstructure. As we have seen, we can control the microstructure by controlling the cooling rates. Then we can produce functionally graded materials using beam deposition, and then it is capable of producing directionally solidified and single crystal structures, again by controlling the cooling rates and the heating rates. And then this can be used for effectively repairing and refurbishing defective and surface damaged high technology components. Okay, so basically the laser cladding process. Now certain drawbacks are that it is having a poor resolution and a poor surface finish. So this process particularly has some poor resolution and poor surface finish, and have very slow build speeds of 25 to 40 grams per hour, which is really very slow. And accuracy better than 0.25 mm and surface toughness of less than 25 mm are difficult with many of the processes of beam deposition. So now let us move to the materials in rapid manufacturing. So we have seen some enabling features of materials, that is like the features of the material that enable them, that enable us to employ them for uh, rapid manufacturing. So first is viscous flow. It is important for processes where a material is in the molten state. So for example, in extrusion based processes, your material is changed into a molten state. So where there is your shear stresses and shear strains employed in the regions. So controlling controlling the viscosity becomes important to control uniform deposition. of the material. And this viscosity is dependent on temperature as well. So we need to maintain an optimum velocity. Too low velocities will cause the materials to flow uncontrollably, and too high viscosities will not enable them to flow. Instead, it will induce a lot of shear stresses. So an optimum low viscosity should be maintained so that they flows in a controllable manner. Okay. Then we have photopolymerization, which is basically employed in stereolithography processes, wherein some photoinitiators initiate the polymerization reaction on interaction with UV light. So we have photoinitiators which initiate polymerization on interaction with UV light to develop a solid part. Then we have the sintering, which is a time dependent consolidation of powder particles. So in many rapid manufacturing processes, the sintering is employed. We have seen selective laser sintering, etc., as the processes where the sintering occurs. So for sintering, we need a reduction in total surface area. Okay, for densification, which is the driving force for densification. Okay, so this sintering is important for consolidation of powder particles, and it is a time dependent phenomena. It is a time dependent phenomena. So we should make sure that processes which are employing sintering should have powder particles who can undergo this reduction of surface area. Then we have this infiltration. Infiltration is a technique basically which is used for increasing the end use properties, and it is basically used to densify the RM paths with a secondary phase. Okay, so suppose you have some porosities, then you can just employ some secondary phase and densify it. So that is what is meant by infiltration. Now different materials for rapid manufacturing processes are materials, metals, polymers, ceramics, composites, glasses. In metals you can have titanium, okay, stainless steel, aluminium. Then you have high performance alloys like Inconel, cobalt, chrome. Then you can also process precious materials like gold, silver, platinum, palladium. Okay, so they can be processed using EBM, SLS, SLM. All these kind of processes, metals can be produced. Okay, or FDM as well. Now comes polymers, ABS, which is acrylonitrile butadiene styrene, polylactic acid or PLA, nylon, which is a flexible material, then polycarbonates, then PVA, polyvinyl alcohol, which is soluble in water, and then thermosets. So they can be processed using techniques like stereolithography, FDM, 3D printing, or that inkjet or binder jet printing, SLS, laminated object manufacturing, etc. Then you have ceramics, wherein you can have them in the powder form or in the form of slurry, which is silicon carbide, porcelain, alumina, etc. They can be processed using 3D printing or SLS. Then you have glasses similar to ceramics using 3D printing and SLS. And then you have composites of metal matrix composites, wherein you can have particulate composites, fibrous composites, or functionally graded materials as well. Now, certain properties of RM parts. So, mechanical properties we have. So, for mechanical properties, you have strength. Strength can be controlled by controlling the microstructures and all. So, we can control the using porosity. Okay, stiffness can be tailored, ductility can be tailored, fatigue strength can be tailored. Then rapid manufacturing objects are usually optically transparent and they can be processed as translucent for some biomedical applications. And then electrical properties of these rapid manufacturing parts are more or less similar to the traditionally manufactured components, and they are majorly governed by porosity, which influences the path of travel of electrons. So, different materials and their additive manufacturing aspects, their properties, how they can be processed using different techniques were discussed in this week's lecture. So, and how these properties can be tailored by tailoring the various process parameters of rapid manufacturing techniques was also looked at during this week's content. So this was just a brief summary of this week's content, and you can study them in depth using the lectures. So we'll now quickly move on to some of the sample problems from this week. So the question 1 from the sample problems is, the dash processes enables the creation of parts by melting and deposition of material from powder or wire feedstocks. It is beam deposition, extrusion, 3D printing, and none of these. So we'll see first extrusion and revisit some definitions. So if any one of you would like to answer what kind of material is used in extrusion based processes? Would anyone like to answer? Okay, so in extrusion based processes, we basically used filament or wires, which are then converted into molten form, and extruded through a nozzle. And in 3D printing, we use ink based forms, okay, which are deposited in the form of droplets. And in beam deposition, we use both powder or wire, which then interacts with the laser and melts. So the correct answer is beam deposition. Question 2. Beam deposition processes use some form of energy focused into a narrow region which is used to heat a material that is being deposited. True or false? So this is true. We have seen how a laser beam, so suppose this was your laser beam, focusing optics. Okay, then this becomes your focal, this is your focal plane, and these are your buried region, this is your exposed region. So you see, this energy is being focused into this narrow region, and here heat is being generated to form melt pool of the fed powder. Okay, so the answer is true. It uses some form of energy, so it can be either laser, light, electron, plasma, ions, etc. Now, question 3. Complex 3D geometries require either support material or a multi-axis deposition head. True or false? So this is true. So either they require support material or multi-axis deposition head is 4 or 5 axis deposition head, which enables the formation of complex free-form surface objects. Alright. Next, question 4. The resulting parts attain low density during the build process in beam deposition process. So the answer is false. We have seen the parts are high density, or rather fully dense parts that can be made using beam deposition process. Okay, so next question. In laser based metal deposition, the deposition could not be controlled by relative motion between the substrate and the deposition head. True or false? So the answer is false. We can actually control the deposition by the relative differential motion between the substrate and the deposition head. Alright, next question is, the kinetic energy of powder particles being fed into the melt pool is dash the effect of gravity on these powders during flight, equal to, lesser than, greater than, or none of these. So we had discussed this during this lecture as well. It should be greater than. Because of the buoyancy effects, in the melt pool, there are density differences. Now, as a result, powder particles may move out. So, hence incoming powder particles hit them and cause them to flow back into the melt pool. Okay, So question number 7. If the substrate is very large or heavy, it is difficult to control the motion of the deposition head than the substrate. So this is false. If the substrate is large or heavy, it is difficult to control the substrate. Rather, it is easier to move the deposition head. Okay, so it is difficult to control the motion of substrate than the deposition head. So question 8. In laser-based metal deposition, the laser generates a small molten pool on the substrate as powder is injected into the pool. This is true. This is what the basic principle of laser-based deposition process is. So question 9. At lower cooling rates, the grain features could not grow and does not look like cast grain structures. This is false. So at higher cooling rates, they cannot grow. The grain features are not able to grow. All right. Last question. The beam deposition process can utilize both powder and wire feedstock materials. So answer is true. So these were some of the questions for this week. So I hope they were clear to everyone. So if anyone has any questions, they can raise them. Okay. Okay, so this lecture video and these presentation slides will be available to you using Google Slide, Google Docs, Google Drive links, and YouTube videos. So you can go through them anytime. And you can always post your questions in the discussion forum as well, or you can ask them during this interaction session. So this is the last call if anyone is having any questions. So I think we can end this meeting. Thank you all for joining in. I hope you are enjoying the learning.
Thank you, ma'am.
Thanks a lot.
Thank you.
Thank
Thank
you.
you, ma'am.
Okay. Thanks.